Okay, so today we are going to study what are stationary waves. So basically, stationary waves are those waves, again, by the name itself says they are stationary, right? They are not moving, they're standing. So this means that they are not progressing. We know that transverse waves and longitudinal waves, these are the waves that are progressive waves. However, there is another type of wave known as the stationary wave, and this is that type of wave in which the wave does not progress. So what are these types of waves, like how are they formed? So the main concept of stationary waves being formed is, number one, there must be an incident progressive wave. So take an example of this, like there is a normal rope. So when we start to vibrate the rope upwards and downwards, we know that a wave would be produced because there is this disturbance in the medium. So a wave would be formed, and that is, we know, would be a transverse wave. And this wave would be a progressive wave. So what is meant by an incident progressive wave? Incident means that this wave is moving, is progressing, and is hitting or is being incident on some type of reflective material. So this is a wall on which the rope is attached, and this wall would act as a reflective surface. And then what happens is, first incident progressive waves. Number two, then the incident progressive wave hits at the reflective surface. So hits at the reflective surface, or the better wording would be is reflected, right? So okay, then it is reflected, then what? After this wave is reflected, like this wave is progressing towards the right, and now we see that at this point my wave is being incident on this reflective surface. What happens is another wave is produced that is opposite in direction of travel. So this would be a reflective progressive wave. So when this incident progressive wave hits at the surface, and because there's a reflection, so what would happen is there would be a reflective progressive wave being produced. So a reflective progressive wave is produced. And again, the concept is simple. Like we know that when a beam of light hits a mirror, it is gonna reflect. So this has the same concept. When a progressive wave is incident on a reflective surface, another wave is produced which is opposite in direction, and we know opposite in direction means it is a reflective. And because originally the wave was a progressive wave because it was moving towards a specific direction, the reflective wave would also be a reflective progressive wave. And the most important point, what links these two incident and reflective waves with the stationary wave? That is these waves being superimposed. And we know that when two waves are superimposed, either, and that is basically interference. Superposition gives rise to interference, and we know that it would be a constructive or a destructive interference. And this automatically tells us that. And why again, why would there be an interference? And the reason is we already know that the source is the same. So the type of wave would be the same. The waves would be coherent. They're traveling in the same plane. So we know that all of those conditions that are required for interference are met. Okay, so let's move on. So this would be your typical standing wave. So we got already see that there are some points that are marked with the yellow marker. So, and there's a reason behind marking these specific points, one between two successive points, this and this, here is a point. So each and every point on this wave has a specific name. So the points where we see displacement happening, these are known as points called antinodes. And we could also say antinodal points. Okay, the and the points where there is no displacement, these points, these are known as nodal points or nodes. Okay, so the reason why these points are formed is, again, when we put in the concept of constructive and destructive interference, we know that when in phase points meet, what happens is a resultant wave is formed which has a larger amplitude. When out of phase points meet, we know that what happens after being superimposed is a destructive interference, right? Destructive interference, when in phase points meet, there is a constructive interference. Similar is the case in this stationary wave. So the reflect when the reflective wave and the incident progressive wave meet each other in phase, so when the particles are in phase, so what happens is they form a wave that has maximum displacement at their nodal points, and if they meet out of phase, then we know what would happen. This would be a straight line. And stationary wave has one property, that is, again, they don't progress towards any direction. The specialty of this wave is that antinodal points are the only points that are able to move, that are able to displace, and nodal points are those points that do not show any displacement. The nodal points are those points that remain stationary, they do not move at any point in movement of that stationary wave. So what happens is, here's a wave, and here's a part of a wave, of a stationary wave. So what happens in stationary wave is that these nodal points, these are the only ones that move up and down. And there's one property that stationary waves, points that are antinodes, they are the only ones that displace, and they displace vertically. And again, the direction of the wave moving is also not towards any towards right or towards left, but rather the wave moves up and down. This is a special case of stationary wave. Okay, so there was one point in stationary wave that distance between two successive antinodes or two successive nodes, either it's this or is this. So distance between two nodes, successive nodes, or two successive antinodes is equal to half of the wavelength. And this is a fact, um, that the distance between antinode and two successive antinode is half the wavelength, and you could easily see how is it half a wavelength. So if we make a complete wave, and here is an other wave, so we could easily see that this is our nodal points. So see, one semicircle, so this tells us half lambda, half the wavelength. So a wave is like this, a distance from here to here will be half the wavelength. So now it's proven, right? Why distance between two successive nodes and two successive antinodes is half the wavelength. Okay, so moving on, there were some key points to remember. So what happened is that when we have a source and then there is a reflective surface, again, the reason why there's a reflective surface is, without a reflective progressive wave, there won't be any interference between the incident waves and the reflected waves, and so there would be no stationary waves produced. So there's a source and there is a reflective surface. So this is a concept in stationary waves, and this is a rule that whenever there is a closed surface at that specific point, a node will always and always be formed. And the other point is that wherever the source is at that specific point, always and always an antinode would be formed. So that was the concept, that whenever there's a closed surface, the stationary wave would form a node. So here, and whenever the part of the stationary wave that is just with the source, at that point there would be an antinode. So no antinode, node, node, and antinode. Okay, so again there were some concepts that were remaining. So we know that v equals to f lambda, and let's say that we have an assumed velocity of wave that is 40 meters per second, and here is a scenario in which there are two closed surfaces. So we would keep our concept in mind that every time a node would be produced on the closed surface. So what happens is, this is the basic type of wave, right? A node and then a node, and that's it. And we join those 2 points. And it is given that the distance between these two closed surface is 2 meters. The length is 2 meters. So keeping in mind that distance between two successive nodes or antinodes is half lambda. So we know that half lambda is equals to this specific length, that is 2 meters. And lambda or wavelength is equals to 4 meters. And if we are asked to find out the frequency, so we know velocity is 40, wavelength is 4, and frequency comes out to be 10 hertz. Okay, so what would happen if we increase the number of wave produced in this specific length? Let's say, okay, keeping in mind we have to make two nodes on each side, so a node and again a node. So what could happen is we just make a complete wave, one complete wave. So now what would happen? Again, the length is 2 meters, the velocity of the wave is 40 meters per second. Okay, so now we know that the distance between two successive antinodes or nodes is half lambda and half lambda. Okay, so this is a rough sketch, right? So half lambda. So half lambda plus half lambda would give us 1 lambda. So this tells us that now, after changing the waveform in this specific length, now we have the wavelength that is equals to 2 meters. And if we are asked to find out the frequency will be v equals to f lambda. Velocity is 40, lambda is 2, so frequency comes out to be 20 hertz. And we can already find out the frequency without even calculating. The reason why? Look at it. The number of waves produced over here was half, right? Half the wavelength in 2 meters. Now what happened? That the number of waves produced in this specific 2 meter length is double. So first, half the wavelength was being produced in this 2 meter. Now one complete wave is being produced in 2 meters. So what happened? That my wavelength was halved. So if wavelength is decreased and with a factor of 1 upon 2, so we already know that frequency would increase by a factor of 2, because frequency is inversely proportional to lambda provided my velocity is constant. So if lambda is increased by a factor of half or decreased by a factor of 2, so my frequency would be increased by a factor of 2 in order to get my constant velocity. So if we make three half waves and four half waves to in keeping in mind to make nodes at these specific points, what would happen if we make three waves, three half waves? What would happen? Again, see, look at it. What would happen is now three times the original number of waves produced. So at first there were half waves, now there are 1.5 waves. So 1.5 wavelength is equals to 2 meters, and my original wavelength would become 4 upon 3 meters. So what is happening? In this case, my frequency would increase by a factor of 3. Initially it was 10, so times 3 will be 30 hertz. So this is the concept, and specific names are given to these specific scenarios. So whenever there's a lowest possible frequency, in this case we know that because see the first and the lowest possible frequency in this scenario is when we make a node over here and a node over here and make a single half wave. So lowest possible frequency is known as the fundamental frequency, the fundamental frequency. So when we increase the frequency, keeping in mind again the nodes over here, and then we got the answer of 20 hertz. So this was the next possible frequency that was to be greater than the lowest possible frequency, and this is known as the first overtone. So on and so forth. The third possible frequency that is to be greater than both the first or the fundamental frequency or the lowest frequency and greater than my first overtone or the second frequency, that is my third frequency, that will be of 30 hertz, and this would be known as my second overtone.